Our topic for today under the chapter of single layer perceptron is linear least square filters. But before we discuss about this, we have to complete our unfinished discussions related to the earlier unconstrained optimization approach, that is the Gauss-Newton method. I mean, we had gone up to some expressions, but I mean, before we start from the point where we had left yesterday, I mean, we need to also discuss about I mean, some of the clarifications, because at the end of the class when I was talking to the students, I could realize that there are a few things which required clarifications. Now, one of the clarifications is related to the error expression that we had put forward, and I mean, some of the students were interested to know that what is the significance of that error expression. So, let me go about that. See, what we have done is that we are taking n number of observations, right. So, with a fixed set of weights, I mean, we are keeping the weight fixed, and then we are I mean, computing the error for n number of observations, and those errors we are designating by E1, E2, E3, etc. up to En, and then we are I mean, defining the cost function as summation of half of Ei square. So, where I is summed up from 1 to n, which is the number of observations, and then we are I mean, our objective will be to minimize this half sum of Ei square, or minimizing Ei square summation in fact. So, to do that, what we did was that we had derived an error expression, okay, so that I mean, with the change of weight, because what we are doing is that at the end of n observations we are going to update the weight, and the thing is that once you update the weight, okay, then the errors that you had obtained for the n observations, those errors also change, isn't it? Because with the change of weight, error is a function of the weights. So, when we change the weights, that time the error also changes. So, the error gets updated. So, what we are doing is that we are operating the whole thing. I mean, we are making a search at the point W is equal to Wn, okay, because the weights are going to change. So, at this point W is equal to Wn, when we are going to find out a new weight, okay, there we are finding out that with the change of weight that takes place, change of weight is definitely going to be W minus Wn, where W is going to be the new weight and Wn going to be the older weight. So, with W minus Wn being the incremental weight, the new expression for the error that we are going to get for the I mean, we are going to get new error components for each of the observations that we already had. So, let us say that for the ith observation, the updated error that we must have is is E, which will be expressible as a function of I and W. So, I means that here we are considering the ith weight, and then the W, which is the weight, and this is equal to Ei plus dou Ei dou W vector, okay, and this will be evaluated at W equal to Wn, right, because that is the point from which we are going to change the or update the weight W minus Wn, right. So, is this, so this we have to update for all these I's, all these observations we have to update the error expression. So, this is the updated error expression, and then what we are going to do is that for the n plus 1th weight we must put forward the minimum value. I mean, we must find out the minimum value of this expression, half of E prime n W vector norm of this square, and the minimum, the W vector corresponding to which it gives the minimum, that W vector we are choosing as the updated weight. So, our objective is to minimize this sum of the squares expression. So, this is what we were doing. So, those who had any doubt about the I mean expression that we had written, I think will feel clarified now that this is the change of the weight that we are making, and then accordingly, since we are changing the weight, we also need to change the error expressions that we had obtained. So, EI was the old error and EIW that we have written on the left hand side is the updated weight. Followed. So, that is clarification number 1 that some of the students wanted, and the second clarification is related to the multiplication that we had carried out. In fact, the expression that we had obtained, I mean for this equation only, okay, the expression that we had obtained in the matrix form was written as E n W, okay, equal to E n, which is the older error, plus J n. In fact, it is the J n which directly gives you the Jacobian matrix, and it signifies the partial derivatives, okay, or the derivative with respect to W vector, which in turn I mean in the matrix it translates to the partial derivative with respect to all the different components of W's, and then it is J n multiplied by the change in weight, which is nothing but W minus W n. So, this is what we had obtained, and in fact, let us say that this is equal to C, this is equal to A, that is this one, and this is equal to B. So, we are having C is equal to A plus B, where all these things, I mean C, A and B, these are vectors, mind you, okay, these are all m dimensional vectors. Okay. So, then any doubts from the students? No. Okay. So, in that case, C vectors transpose will be equal to A vector plus B vectors transpose, okay, which will be nothing but A vector transpose plus B vector transpose, right. So, when we are going to compute C vector transpose times C vector, the dot product of these two, if you are going to take, then it means that we have to take A vector transpose plus B vector transpose multiplied by A vector plus B vector, the dot product of this. So, if you expand this, then what happens is A vector transpose A vector plus A vector transpose B vector plus B vector transpose A vector plus B vector transpose B vector. Now, that means to say that we get 4 expressions. In fact, that is what people were pointing out to me, that we definitely require 4 expressions here. One is A by A, which ultimately will turn out to be norm of A square, is not it? This will turn out to be norm of A square. This will turn out to be norm of B square. In fact, this B itself is a product of these two. So, B that we are writing is already a dot product of J n and W minus W n, okay. So, J n is actually a matrix, okay. This is an n by m Jacobian matrix, and this one is m by 1 vector. So, in effect this becomes an n dimensional vector. In fact, all these things, each of these things are n dimensional vectors. So, not m, but n dimensional vectors. Now, the question is about these two terms, okay, these two cross terms, that is A transpose B and B transpose A. Now, these being vectors, A vector and B vector being vectors, okay, they are all going to be equal. I mean, both of them are going to be equal. Why? Because A transpose B means what? A transpose B simply means, I mean, if it is n dimensional vector, let us say, in that case this can be written as summation I is equal to 1 to n, because this is n dimension, and if A vector composes of the terms ai, bi, a1, a2 etc. up to an, and B vector consists of b1, b2 up to bn, then it will be summation ai, bi, okay, I is equal to 1 to n. And similarly, B transpose is definition also is this, I is equal to 1 to n ai, bi, I mean BIAI, but it's is the same in this case. So, both these things are equal, okay, and that is why whenever you are trying to get a C transpose C vector, that is equal to A transpose A vector plus 2 times you can write A transpose B vector, okay, plus B transpose B vector. Okay. So, that is how we arrive at 2 terms. In fact, what we are doing is that we are multiplying everything by half, so that we get here half term, that means to say that here we will be getting half norm of C square, and here we will be getting half norm of A square, okay, and here we will be getting this term. There is no half associated with it because it was already multiplied by 2. So, when half comes in, it becomes multiplied by 1. So, here this term remains as the A transpose B, and then this term is B transpose B, which is which should have been norm of B square, but because this itself is a multiplication, so this itself is J n W minus W n. So, what we are going to write as B transpose B is W minus W n transpose J n transpose J n W minus W n, right. So, that is what we are going to get. So, B transpose B also will be written in that form, so that in effect we are going to get 3 expressions. So, that was a doubt which some people had, that I mean we are multiplying these 2, but then instead of 4 terms we are getting 3 terms, but if you are looking carefully, this term that you are getting A transpose B, here the coefficient is 1, that means to say that those 2 equal terms have been combined. So, that is why it leads to, I mean when we substitute for C, A and B, we substitute the I mean expressions that we had considered, okay, because for C we have to put forward this, A equal to put forward this, and B equal to this. If we do that, then we are getting this expression very easily. In fact, I mean I would like all of you to verify this yourself, okay, and feel convinced about it. So, this is norm of E n W square is equal to half norm of E n square plus the second term is going to be E transpose J n W minus W n. Okay, this is very clear. This is the A transpose B simply. Okay, and then the B transpose B, and B transpose B in this case is going to be half of W minus W n, this whole transpose J transpose n J n W minus W n, right. So, this is the expression that we are getting for B transpose B. So, this is the term that we had obtained. Now, what we are doing, this whole thing we are now differentiating with respect to W vector. So, the result is pretty simple. Now, here all these things, mind you, will be differentiated. So, this is actually a scalar expression, okay, and this we are multiplying. I mean this we are differentiating with respect to W, right, and then what happens is that this term is there, okay, and then this expression is going to be equal to 0. Then whenever you are differentiating this with respect to W vector, okay, then it is a differentiation of this form, isn't it, X transpose W vector, okay. This is an expression of this form, the second term I mean to say, for which we already know that the result of the differentiation is X. So, that is why if you are taking this to be a transpose form of expression, okay, then whenever you are differentiating with respect to W, then what is it that you are going to get? You are going to get J transpose E, very correct, J transpose E is what you are going to get, and then here what is it that you are going to get out of this term? Okay, you are okay. this thing, if you look at it, this thing is a quadratic form of expression, isn't it? So, we are having W minus Wn, okay. Let us call it something, let us call it as y. So, half of y transpose, okay, and this one we call as R, okay. The R matrix it becomes, because here this is going to be an m dimension, m by n matrix, okay, and Jn is going to be n by m matrix, right. So, in effect it is m by m R matrix that it becomes, and then this becomes y. So, this is a quadratic form of expression for which the derivative is going to be R y, okay. So, that is what we are going to write, and then this will be equated simply to 0, okay, because what we are doing is that we are going to minimize this expression. So, we are finding out the derivative with respect to w and equating the derivative with respect to w to 0. This is what we are getting, okay. J transpose n E n, okay, plus J transpose n J n W minus W n, okay. This is equal to the 0 vector. Is it very clear? Okay. I mean, we are going to get that. How are we getting J transpose E n? J transpose E n simply we are obtaining from the second term, and what we are obtaining from this is this R y form. So, R y form means we are going to get, this is the R. So, we are writing it directly, J transpose J, and then this is our y. So, y also we are writing, okay. This whole thing should be equal to the 0 vector. Is it okay? So, that means to say that if we now take this on the right hand side, then we are going to get J transpose n J n, okay, multiplied by W minus W n, okay, that is going to be minus of J transpose n E n. All right. Now, if we pre-multiply the left hand side and the right hand side by the inverse of this product matrix. Now, this is a square matrix, okay, and let us assume that it is non-singular, okay. So, what we are going to do is that we are going to take inverse of this product matrix, J transpose J product matrix, we pre-multiply by that. So, that will give us W minus W n equal to J transpose n J n, this product's inverse, right, times J transpose n E n. Is this clear? Just multiplying the left hand side and the right hand side by this matrix terms inverse. Minus sign, very good, yes. So, people have rightly pointed out that there is a minus sign over here. So, that is why the expression that we are getting for the updated W, I mean instead of calling it as W, we are now going to call it as W n plus 1, is not it, because this is the updated W. So, W n plus 1 is W n minus J transpose n J n whole inverse J transpose n E n, right. So, this is a very important relation that we have got, and this is the pure form of Gauss-Newton method. So, this is the Gauss-Newton method in its pure form. Right. Now, that means to say that using this expression, it should be possible for us to calculate the updated weights, and all we need to know now is that the knowledge of the Jacobian matrix. this must be known to us, okay, because only then we will be able to compute this. But is the computation of this always guaranteed? Because we have in this case made an inherent assumption that J transpose J is going to be a non-singular matrix, and that is why its inverse exists, okay. And with that assumption we have proceeded. Now, one thing which can be shown that this J transpose J matrix that we are getting, okay, here all these are matrices. So, this J transpose J that we are getting, it is definitely a non-negative definite. It is J transpose J is non-negative definite always, okay, but there is no hard and fast guarantee about non-singularity, okay. In fact, it will be non-singular only when this J transpose J is having a rank equal to n, rank equal to its row, that is n. So, if this J transpose J happens to be rank deficient, then J transpose J could be singular, and in which case the inverse will not exist. So, it is not always guaranteed that for every n, okay, for every n there is no guarantee that J transpose J is going to be non-singular, okay. So, there is a risk that it becomes J transpose J becomes rank deficient, and what we need to do is to modify this slightly, okay, so that the rank deficiency is taken care of, okay. So, in order to correct for the rank deficiency, what we do is that we simply add something to this J matrix, I mean this product matrix, that is J transpose J. So, to that we add a diagonal matrix, okay, which is of the form delta I, okay, I being the identity matrix, and we are multiplying that identity matrix by a constant term delta, okay. So, delta, actually we have to choose delta as a small positive constant, okay. So, delta is a small positive constant. So, in this case delta I becomes a diagonal matrix. So, what we are going to do is, in order to correct for the rank deficiency of J transpose n J n, okay, we are adding this diagonal matrix to that. So, instead of taking J transpose J, we are going to take J transpose J plus delta I, okay. And in fact, this small positive constant is chosen so that this J transpose plus delta I is ensured to be positive definite for all n, okay. So, if we can choose a small positive constant such that this J transpose J plus delta I is going to be positive definite for all n, in that case our job is done. So, what we have to do is that if this remains as positive deficient, then simply in this expression that we had got for the Gauss-Newton method, all that we need to do is this term J transpose J, which should be replaced by J transpose J plus delta I, okay. So, if we do that, then this is the expression that we are getting as the modified form of Gauss-Newton method. Which is W n plus 1 equal to W n minus J transpose n J n plus delta I inverse J transpose n E n, all right. So, this modification that we have done effectively is a solution of this equation, okay. The cost function CW, actually we were earlier solving C is equal to half of summation I is equal to 1 to n E I square. Okay, this is what we were solving earlier, but now what happens is that it becomes a, I mean because of the introduction of this delta I, it becomes a solution of delta times norm of W minus W 0, where W 0 is going to be the initial value of the weight vector. Okay. So, this square plus this term plus this sum of the squared errors. So, effectively it is a minimization of this expression, where W 0 is the initial value of the weight vector. Right. So, here what you see is that as we increase n, okay, as we increase the value of n, then this term, that is sum of E I square, this will be more and more dominant as compared to this one. So, the effect of this could be neglected, okay, as you go in for larger and larger values of n. Okay. So, this method is applicable, and now with the knowledge of Gauss-Newton method, okay, we have learned how many? 3 optimization techniques, right. Number 1 is the simple steepest descent method. Number 2 is the Newton. So, simple steepest descent method was nothing but the first order approximation of the Taylor series expansion. Then the second optimization approach that we had studied is Newton's method, which made use of the second order terms of the Taylor series expansion, that is minimization. And now we come to the Gauss-Newton method, where as the cost objective function we are keeping the sum of error square and we are minimizing that. So, this is what we have got as the optimization tool, and the reason why we have got all these optimization tools with our disposal is that we are ultimately going to use the perceptron as a linear adaptive filtering problem. Okay. In fact, I mean this is quite simple to understand. You see, a simple perceptron model would look like this, isn't it? That say this is the neuron, okay, and we are going to have an m dimensional input, right. So, these are nothing but x1, x2 up to xm, okay, forming an x vector, and then we are going to have the weights as w1, w2 up to wm. Okay, we are going to call that as the weight vector, the input as the x vector, and then we are going to have an output of this, okay, which will be in the form of y. So, y is going to be nothing but either you write as x transpose y, or you I mean x transpose w, or you write as w transpose x, whatever, and then this will be compared against some d, isn't it. So, there will be a comparison that we are going to get between the d and the y. D is the desired response. Okay. So, if I take any vector xi and we obtain yi, then the error that is going to be yi minus di or di minus wi, and then this error that is there is going to change all this set of weights again. Okay. So, this system ultimately adapts, I mean with the change of weights the system will be adapted to give the the actual output to be as close as possible to the desired output, I mean doing the error minimization. So, that is why this can be looked upon as a linear adaptive filtering problem. Okay. And in this linear adaptive filtering problem, okay, the kind of functions that we are going to use are pretty simple ones. In fact, right now we are going to study about the linear least square filter approach. Okay. So, linear least square filter, in fact what we are going to do is pretty simple. Okay. We are going to consider two things. First is a single linear neuron. Okay. I mean, following our perceptron model, we are going to take a single linear neuron that works according to the equation y is equal to x transpose w or w transpose x, whatever, and in the cost function of that, okay, you use the sum of error squares. I mean, as we have taken just now. Now, we have already taken the sum of error squares in our Gauss-Newton approach discussion, okay, but we did not use there any single linear neuron, because we were only considering the cost function optimization approach. I mean, earlier our emphasis was only on the cost function optimization. We I mean, temporarily forgot about neural network, but when we are designing a linear least square filter, we are going to consider a single linear neuron. So, where we are going to make use of this expression, okay, because it is linear. So, now in this case, I mean, so linear least square filter will use both the single linear neuron as well as a cost function of this nature. Now, the error vector E n in this case can be simply represented as what? As d n, I mean, where n again is the number of observations, right. So, error for the n observations, okay, I mean, the nth observation is E n equal to d n minus, I mean, in fact, we are writing directly in terms of vector only. So, E n vector, which will include E 1, E 2, E 3 up to E n, okay, which is equal to d n vector minus, this will be x 1 vector, x 2 vector up to x n vector, transpose of this times w n, right. So, this is understood. So, d n again is the desired response vector. So, this we are going to write in the form of d n minus, we are introducing x matrix over here, x n w n, where the definition of this x matrix is this x n is the n by m data matrix. Is the n by m data matrix defined as x n will be nothing but x 1 vector, x 2 vector, so on up to x n vector transpose, means this one. Okay. So, n by n means what? Here each of these, so I mean, if you take the transpose of this means in the column we will be getting x 1 vector, x 2 vector like that, and each of these vectors is going to be an m dimensional vector, and there will be n such vectors in the row. So, there will be n number of rows, and the columns will encompass the elements of each of the vector. So, since there are m elements, so there will be n rows and m columns. So, x n is going to be a complete data matrix that contains all the observations, all the m observations are contained into it, and then d n is going to be simply the data vector, I mean the desired responses, okay, for each of the observations. So, here d n is simply defined as d 1, the vector containing d 1, d 2 up to d n, this whole thing transpose. Okay. Now, this equation that we had obtained, okay, that is E n equals this, okay, let us call it as equation number 1 for today. Okay. Now, if we differentiate this expression with this equation with respect to w n, then what we are getting? In that case, we are going to differentiate this with respect to w n, and differentiating this with respect to w n gives you what? The gradient of the error vector. The gradient of the error vector is what we are going to get, okay. And what will be the differentiation of this term? 0, because dn is independent of w. And what will be the differentiation of this expression? Minus x transpose n. Very good. This is going to be minus x transpose n, because this is the expression of the earlier form, okay. I mean it is of the form x transpose w already. So, x transpose this transpose is going to be, so x transpose itself will be this term. So, that whenever you are ultimately deriving the solution, then it will be transpose of this expression. So, in so differentiating, so what we are doing, that differentiating equation 1 with respect to the w vector is going to be grad of E n, okay, grad E n, which will be equal to minus x transpose n, right. And as we already know that the Jacobian matrix is going to be the transpose of the gradient matrix that we had derived in the last class, all right. Gradient matrix, because gradient matrix is what? Gradient matrix is simply going to be the n by m matrix, isn't it? Whereas the Jacobian is going to be m by n, right. So, it is just the transpose of that. So, that is why the Jacobian matrix J n is going to be what in terms of x? Minus x of n, minus x of n, because we have to take the transpose of the gradient matrix. So, transpose of the gradient matrix means transpose of this once again, means we are back again to x n. So, J n equal to x n, and what we are simply going to do, I mean this is a very interesting expression that we have got, all right. And now we are in a position to, I mean this relation, how did we obtain? We obtained it from the Perceptron equation, simple Perceptron equation we had obtained, that the error term is equal to x into w, x being the input. So, this x into w is the Perceptron expression. So, we had I mean defined the error that way, d minus x times w, and this is what we had obtained by simple differentiation, that now the Jacobian is already obtained, and because we obtained Jacobian, now we can substitute this Jacobian expression in terms of this input vector into the error expression that we have got. So, we should substitute this in this weight updating equation. So, let me just find out the place where I had derived this. Yeah. So, in this equation which we had earlier obtained as Gauss-Newton method in the pure form, here instead of j we can write minus of x, agreed. So, if we write minus of x in terms I mean in place of j, then what we are going to get as the expression for w n plus 1 is as follows. Okay. I am going to write it down and you please take time to verify that. W n plus 1 is equal to W n, okay, and then what we are going to do is that we are going to do two things. You see, we have got an error expression here, that is E n, and E n mind you is d n minus x n W n, okay. So, we are going to substitute this equation, okay, in place of E n, over here, and in place of J n we are going to substitute minus x of n, okay. So, if we do that, then we are going to get W n plus 1 is equal to W n already is there, and then we are going to get I mean because already a minus is there, I mean the Jacobian term is going to be a minus of x of n, okay. Now, here there is already a Jacobian term, so which will be equal to minus of x transpose n, Okay. So, we can write down this. So, this minus and minus makes it a plus. So, it will be W n plus, now this term we had J transpose J, which is going to be X X transpose, which will be X X transpose, inverse of that. So, this will be X X transpose, inverse of that, okay, X transpose n, okay, multiplied by, now this will be X transpose X, X transpose X, inverse X transpose n, and here instead of E n I am writing d n minus X n W n, okay, right. So, this is what we are getting. Now, something that you can see, so this is equal to W n plus, what is it that we are getting? We are simply getting X transpose n X n, okay, this inverse X transpose n d n, okay, minus what are we going to get? We are going to get this expression X transpose n X n inverse X n, okay. Now, X transpose n X n W n, okay. So, this inverse and this direct. So, what is it going to be? Identity, and then this multiplied by W n means this term becomes equal to W n. So, what is happening? This is plus W n and this is minus of W n. So, that is why this term and this term are getting cancelled with each other. So, then we are getting the net expression as X transpose n X n inverse X transpose n d n, okay, as the new expression for W n plus 1. Now, this is very interesting. You see that earlier we had the W n plus 1's expression written in terms of W n. That means to say that W n plus 1 we would have obtained iteratively, means we needed the previous value of W in order to compute that. So, it was a recursive form of relationship that was established earlier, okay. Whereas, this expression can be computed using single iteration, isn't it? Because all that we require is the nth input data, okay, and if the nth input data is available to us, we can compute, okay, what the n plus 1th weight is going to be. So, W n plus 1 in this case is expressible directly in terms of this. Now, this expression, okay, that is X transpose X inverse, this whole inverse times X transpose, okay, this term is recognized as the pseudo inverse of the data matrix X n, okay. This is the pseudo inverse, this is recognized as the pseudo inverse of X n, okay. In fact, there is a proof for that which some of the researchers had already shown, okay, that this is recognizable as the pseudo inverse of X n, and we are going to indicate that as X plus n, this being the pseudo inverse expression. So, that is why here we are going to get the solution as W n plus 1 equal to X plus n, which is the pseudo inverse of X n d n, right. So, we are going to obtain W n plus 1 as the pseudo inverse of X dn, right. So, the weight vector, so thus the weight vector solves the linear least square problem. Problem defined over the observation interval n. All right. So, now what we are going to do is that we are, so this is a form of expression that we have obtained, and we are going to take a limiting form of the linear least square filter. Okay. So, we are going to take a limiting form of this limiting form of linear least square filter, and that is called as the Wiener filter. Okay. In fact, we are going to obtain this limiting form as n tends to infinity, but in this case the assumption that we have to make is that if you are taking this x and d to be a random process, okay, because x is the input, d is the desired response. So, x and d, if you take it to be a random process, then we have to assume that this is following an ergodicity property. Okay. So, I am not too sure that if you as well as the distant viewers are having some background related to the stationary and ergodic process. So, that is why I mean we can spend just a few minutes to explain that what the stationary process and ergodic processes mean. Okay. So, we will briefly cover that, and then we will go over to the Wiener filter design aspect. Okay. Now, let us take a process x of t, okay, and then we take any single realization of this process. Single realization we are calling as x of t. So, then what happens is that this x of t is nothing but a sample function of the process x of t. So, this is the process, and a single realization of that we are going to call this thing as a sample function. Okay. It is as if to say that you have got one random variable x, okay, supposing in the form of vector you have got a random variable x1, x2 up to xm, those are its elements, but you have got a random variable and you take a single you collect the samples of those variables. Let us say that x vector 1, I mean x1 to xn, these you take. Okay. In that case, this x1 vector, x2 vector up to xn vector, what you have taken is actually a single realization, a single instance of the whole process x. You cannot capture everything, isn't it? You have only made n number of observations, okay, and you have only collected the n number of points out of it. So, this x1 to xn, the function that it covers can at best be described as a sample function. All right. Now, we define two quantities. First is that what is a stationary process. Okay. The definition of stationary process is that if the ensemble averages are independent of time. just to understand the thing in a very qualitative sense, that stationary process is something where the statistical characteristics do not suddenly deviate. Okay. I mean, you take the ensemble average now, and you take the ensemble average and you take the average at some later instance, okay, then that is not going to vary. Okay. So, drastically there is no change in the statistical characteristics. So, that is being defined as a stationary process. So, in fact, the stationarity assumption always we have to make in I mean realization of this, because what the inherent assumption that you are making is that when you are collecting the training samples, when you are collecting XIDIs, okay, you are deriving this XIDIs out of a stationary process, okay, and you are also going to use it in a stationary environment. If you are not going to use it in a stationary environment, then you have to I mean all the time train it, you have to make it adaptive. Okay. So, this is the stationary process definition, that if the ensemble averages are independent of time, and ergodic process means that if the expected values can be calculated by averaging only one sample function. That means to say that here the n observations that we have made, okay, that is one sample function, and if you can calculate the average, I mean if you can calculate the expectation based on this one sample function observation only, okay, then that will be described as an ergodic process. Okay. So, the definition of ergodic process says that if expected values can be calculated by averaging one sample function in time domain. Okay. So, now can you tell me, is ergodic process a stationary process? Yes or no? Definitely yes. All right. All ergodic functions are going to be stationary, because you are in this case saying that using one sample function in time domain itself you can calculate the expected values. So, all ergodic processes are stationary. But all stationary processes are not ergodic. All right. So, what we are making as the assumption is that we are drawing this x vector and the d, okay, from ergodic environment. Okay. So, our assumption is that x I and d I are drawn from ergodic environment. That means to say that whatever expectations we get, okay, that should be derivable from this sample function itself, XIDI's sample function. Okay. Now, this kind of environment is actually described by second order statistics. So, we define some second order statistics for this ergodic environment, and those second order statistics are firstly the correlation matrix of Xi. In fact, correlation matrix will be defined as, I mean we will be indicating by the matrix Rx, okay, and The other second order statistics that we make use of is a cross correlation between this xi and di. So, this will be the cross correlation vector between xi and di, and this will be denoted by rxd. Okay. So, these two quantities they define the second order statistics, okay, and we are going to define these terms, okay, Rx. In fact, you must be knowing that in a very simple terms, where I mean we will expand this in the next class, but talking in their basic definitions, okay, this Rx is going to be the expectation of x transpose, right. So, x transpose is what? X transpose is going to be the outer product of these two vectors, okay. So, that is going to be, I mean, an m by m matrix, n by n matrix, yes. So, this is the expectation of xi x transpose, okay. This is the correlation matrix, or yes, this is the correlation matrix, and Rxd's definition, the cross correlation vector definition is that it is expectation of xi di, right. So, these two quantities, in terms of these two quantities, we will try to express the updated weight. So, can we get this updated weight in terms of the correlation matrix and the cross correlation vector between xi and di? That is something that we are going to see in the coming lecture. Thank you very much.